What temperature out there on a Friday? So, Mark Nielsen, are you here? Thank you. And I've adjusted accordingly. Yeah, I did, yeah. That gives me more insight, though. All right, your friendly reminder that, see where are we at? There we are. We'll finish thermodynamics today. There's just the second half, second law on entropy. And we'll review Monday and have a test next Wednesday. Your homework for homework number, what is it, 6? Chapter 17 and 18 is currently due Saturday. 11:59 p.m. So a lot of people are forgetting. So don't. Okay. Something looks different. There we go. So you got to explain to your mom what thermodynamics is, and you tell her what? Or anybody else. That's my generic answer, because my mom doesn't. She appreciates science, but when I start going off, her eyes glaze over. So point is, explain it so that the lay non-scientist can understand. What's thermodynamics? What are you studying today in class, Jimmy? What's that? Go for it, Brandon. Study of heat and how it's transferred and why. Yeah, good. I like it. Yeah. Want to add to that? Anybody?
Well, it's using heat or studying the use of heat to do work.
Yeah, how it can be useful. Studying how heat can be used to do work. Do you want to add to that? No. Okay. Good. And the first law of thermodynamics you remember as what? Conservation of energy. Good. Good. And in terms of heat and work and internal energy, how would you describe them? That first law. You got a system and it has a certain internal energy. There's things you can do to it. Tell me. Okay, I'll narrow it down. You got a system. In terms of heat, what can you do to that system? Oh, come on, help me out here. You have a system. It has a certain amount of internal energy sitting there, which means it has a certain temperature. All right. In terms of heat, what can you do to it? Heat up or cool down. You can add heat or take it away. Yeah. Yes?
When you have a system, if you add heat energy, the work and the difference in internal energy will equal that amount of heat energy that you add.
Very good. Yeah. Yeah, if you add heat to a system, then two things could happen. The internal energy can go up, or you can cause that system to now do work on something else. Because you put energy in, and it's either going into increasing its internal energy or causing it to do work. But they got to balance. And you can go the other way. You can do work on the system. That puts energy into the system. Again, it can increase its internal energy, maybe its temperature. Work could come out, or heat could come out. Just as long as the ins and the outs balance. Conservation of energy. Very good. We ended with adiabatic process. If I write down what I wrote last time for the first law, we just did this. So you add heat, the internal energy can go up. Whoops. The heat coming in can increase this or make make it do work, or any other direction. In adiabatic, in terms of that, you can think of it as Q is 0. I pumped on the bicycle pump and made the water vapor in the 2-liter bottle condense. That happened so quickly when it blew the stopper out that for that brief moment when it was condensing and it did work on the system, Q was 0. You can be adiabatic by having it happen really fast or insulating it really well so no heat goes in or out of the system. So if that's the case and you don't add any heat or take any heat away, whether it's compressing or expanding, then these two are what adjust. So pumping on it, or when it expanded, that gas did work on the system and caused it to condense. But again, energy was conserved. Yeah? Yeah, you open up a can of soda. Yeah, we can approximate. There's actually no real thing as completely, perfectly, ideally adiabatic. But if it's fast enough, sure. And what's happening is the CO2, your carbonation, is trying to come out of your liquid. Oh, yeah, yeah. Did I spell it right? Adiabatic, yeah. And it's one of the bold-faced glossary terms in your book, the pop. They pressurize it to keep the gas in. Think of those gases, bubbles trying to boil. They're not, but they're trying to come out. But if you push on them so that their vapor pressure can't overcome the pressure, they don't come out of the liquid. When you release you open your pop, or this way, the pressure on top decreases. Their pressure is now enough to come out. And yeah, they're expanding, boiling. That's doing work on the system, and there is a change of energy. Yes?
So if you do work on the system but you don't add any heat, the temperature will go down.
No, goes up. You've probably done that. If you got your bike pump, I should repeat that, sorry. If you, tell me if I do it right. You do work on a system, but no heat goes in or out, the temperature should go up, not down. You're pumping your bicycle tire up. If you can do it fast, it's more conspicuous. What does your tire and or the pump get? Especially if you have an air compressor. They get warm. Because you're doing work on the system, right? You're pumping. You're doing work, putting work in. You're putting energy in. Where does it go? To increase the internal energy and usually the temperature. Somebody asked before class, the internal energy can increase without the temperature increasing. Give me an example. Yeah, it was your question. The internal energy of a system can increase without the temperature increasing. Because that's just the average translational. Well, give me an example.
The cooker, high-pressure cooker, right?
High-pressure cooker, or more generically, phase changes. Yeah. Where energy goes in to melt it, freeze it, condense it, evaporate it. But the temperature is staying. If the temperature goes up, does the internal energy go up? Yes, because that's average translational kinetic energy. That's part of the internal energy. So yes. Now you had a question.
Can you pressurize that bottle supposed to know the energy was being produced?
Well, it was less adiabatic while I was pumping because I couldn't do it super fast, but I was trying. It did get warmer, yeah, and you can try it yourself.
And it was emitting some heat, right?
Yes, and it does emit some heat. So in that sense, it wasn't perfectly adiabatic because some heat was leaving the system. But in terms of first law of thermodynamics, I was doing work on the system, putting it in. I like this picture. You got U. You can have Q come in. You can do work on, or you can have it do work, or Q out. Whoop. So in that case, I was doing work on. Some of it was causing the internal energy to increase in its temperature, but yeah, some was escaping as well. When it popped, it had a large enough pressure, it was doing work by the system. Energy was coming out. And it cooled itself off and allowed it to condense. And that one happened fast enough that that didn't have time. Shortly thereafter it did. There's some more hands, yeah.
Last night, I was getting ready to drink a hot cup of tea, and
Thought of the class?
I stirred it to cool it. And I thought, now what am I doing?
Ah.
Am I,
So you got your hot cup of tea and instinctively you wanted to stir it because you knew that would help cool it.
right,
Okay, how does that cool it? How does that help cool it?
I might say it makes more of the molecules of the tea open to the air, and so the air cools down.
That is true. More of the molecule. If it's trying to cool, which ones cool fast if it's just sitting there stagnant? The top ones, they can evaporate, which is a cooling effect for your tea. Well, if they leave, and it leaves the less energetic ones on top, eventually they won't have enough energy to escape. But these down here might. So convection can help get them up there, but stirring too allows them to get to the top, and they're more likely to escape. So stirring gives them a chance, so to speak.
okay, so it's causing it to evaporate,
Yeah.
and then that's,
Well, that's the biggest factor there. They're conducting through your cup as well. That's cooling, but that can happen top or bottom.
because I thought, when I was stirring it, I thought, well, I'm creating more kinetic energy, and that would make
Good, you're right. By stirring, you're doing work on the system. So something has to happen. Either it's going to do work, heat's going to escape, or it's going to increase the internal energy and raise its temperature. And you know, if you insulated your cup well enough, and it's not a heat engine, yeah, it would. But you'd have to do it quite a while. And I've done that with lead shot or copper shot in a tube. And if, say it's a meter long, and you turn it so it falls, give it potential energy, I'm putting work in, raise it up, let it fall to kinetic, it hits, turns to heat. Again. And I've done that like 100, 200 times, and I've noticed the temperature go up. A small amount, but conspicuously. It's easier maybe with an egg beater or your stirrer. If you can insulate it well enough and turn on your KitchenAid for 10 minutes, that you would see the increase in the temperature.
I'm a little confused how the temperature could go up in a system without being added.
No. The temperature can go up in a system. Heat needs to be added. Was that back to my internal energy thing? Internal energy of a system can go up without temperature changing. Phase change, for example. And the only way, I'm going to use it as a teaching moment. There's two ways I can think of for internal energy to increase. Name one. Add heat. What's a second? Do work on it. Pressure, the same. So these two. Okay, that can happen without its temperature changing. It can go into causing a phase change or something. However, if the temperature goes up, the internal energy had to have gone up as well, because that's part of the internal energy. But it won't go up unless you add heat or do work on it. Yeah. So the bicycle is a good one. I'm doing work on it. I'm not adding heat to it, doing work on it. It went to increase its internal energy, which in that case did raise its temperature, because it wasn't making it change phase as I pumped. And as Ines pointed out, some heat was escaping. Yeah. Good, go.
Just to be sure so you're not adding heat, but by working on it, it is heating up. Even though you're not adding heat, you're
Yeah. Even though I'm not adding heat, it's heating up. Yeah, and the confusion might be physics lingo with layman's lingo. Yeah, we say, oh yeah, that's heating up. And what we mean is the temperature's rising. So maybe to clarify, in that case, I'm not adding heat, I'm adding work. Its internal energy is increasing and thus its temperature rises. Which by that we usually mean it's heating up. If you have cold tea and you do work on it by stirring it, first law of thermodynamics says, work went into the system. Well, one of these things better happen. If you can insulate it so that the heat doesn't come out, and it's not hooked up to a motor or something trying to drive anything, then yeah, its internal energy is going to increase. It's not changing phase. It's going to warm up. And you can see that if you insulate it well enough.
Okay, so I'm looking at this diagram here, and you've got heat energy into the system, and you've got work on the system. Is that different, a different factor of work than when you have an equation?
I mentioned briefly last time, if you looked up on the internet, equations they list up for first law of thermodynamics, what is it? You'll get this equation in multiple forms. They're all saying this.
Okay, so how does it work on
But, so you could rewrite it like this. Let's see, if you do work, the internal energy, if that goes up, you could have Q added, or work on. If those are going in, both positive, then that's going to go up. Some people, when they get into this physics, and this is where it confused me, they just put W. It's work. You have to figure out whether it's work done by the system, leaving the system, or work done on the system, entering the system, and use a positive sign or a negative sign. And if that helps you, albeit, I think conceptually this is nicer. That's why I'm doing it that way. Does that help though, you? So in this equation, if this was work on, it should be minus.
Oh, okay, so if you took the work on, that makes sense.
Do you see that? Oh, I better check my algebra before I put my foot in my mouth. Whew, okay, this equation is the same as this equation, just rearranged algebraically. Good. It's just in certain cases, you don't have all four of these happening. But if conceptually you can realize what's going on. I'm pumping on a bicycle, I'm doing work, it's going in, it must be going into the system. Whereas the steam engine, the steam came out and it was, the system was doing work by the system. Because it was causing something to drive. Good questions, and thank you for asking. And if you guys, anybody sitting there going, gee, this is boring, come on. That's what this class is about. I'm glad you're thinking about this and want to understand it. If you ever have more, let me know. Even outside of class. So what's the second law of thermodynamics? We conserve heat energy, but this second law says you don't quite get all of it. Is that where I want to hit? That's why I don't see it. It's on this page. We'll compare. Second law. Then I don't have to rewrite it. That was, I said at the beginning of the last lecture that thermodynamics was kind of based on two assumptions. They didn't look at the nitty-gritty of the molecules. One they saw was, hey, energy seems to be conserved. End result, overview, macroscopically. We just covered that. The second one was what we always observe. The direction heat seems to flow. Do it pictorially. Heat flows spontaneously, naturally, from a hotter object to a colder object. And at this point I want to emphasize, not if the thing has more internal energy to something with less internal energy. It's if something's hotter or colder. What's a drastic example? Big pot of water at room temperature. Big pot. Little cup of your hot tea. Burning hot. Who has more internal energy? The big pot. Why? This is hotter. They're moving around faster in general, on average. There's less of them, yeah. Okay, sure. On average, these have less translational kinetic energy. But there's a whole lot more of them, and so it adds up, and they got more internal energy than this. You put them together, which way is the heat going to flow? To the T to the water, hot to cold. Not more internal energy to less internal energy, from hot to cold. And that's what drives heat engines, everything. And that's the second law of thermodynamics. This is natural. So do you ever expect to see in nature spontaneously happening heat flow from the water to the hot tea? No. Can it ever? Can you make heat flow uphill? With work. And that's the second law. Let's see. I'm going to draw it like this. So you have your hot reservoir. They have these pictures in the book, so I'll stick with them. I like them. A colder reservoir. We just said naturally heat would want to flow down. So in order for heat to flow up, we'll call that Q from the heat from the cold side. In order for that to happen, you have to do work on this system. So work, let's see, well, to get it to go up here, come back down, work on, in, however you want to look at that. Then you can get heat to come up to there. So you do work on the system, and that can get the heat to flow from the cold to the hot, the way it doesn't naturally want to go. That's what the second law says. You just won't do it spontaneously. And I try to draw these to scale. See the width of this? Kind of represents how much heat. If you do work, I guess I didn't complete it there, did I? Whoops. If you do work on it, you can add the two, because energy's going in to get it up. You can't ever have it broad the whole way, because that would violate first law. Energy still has to be conserved. This is energy, this is energy. How much do you get out? They still have to balance. So we can't ignore first law.
Is that also the reason why the T cools down, because the stirring is colder than T?
Oh, you mean the spoon? Yeah, that's a good point. If you have a metal spoon, it's more conspicuous. You put that in your hot tea and you stir. Yes, there is heat transferred to the spoon through conduction, because it's a good conductor of heat. And so some of that heat leaves the tea to warm up the spoon, and that is true as well. Naturally, just sitting there, it wants to cool. Hot tea to colder air, and that'll happen naturally. In order to heat up your tea, what do you got to do? You got to put it back on the stove and apply heat. To make the stove work, you got to do work. So ultimately, it's that. It depends on if you want it to cool or not. If you want it to cool, yeah, use something that conducts heat better, like metal, because that'll help it cool more quickly. If you want to keep it warm, yeah, use like a plastic spoon or wooden stick. And stir gently. The best thing you can do to keep your things warm, put a lid on it. And that stops which method of heat transfer? Not radiation, convection. Because then that hot air doesn't escape and leave away. Yeah, Ryan.
So in that example, when heat is going from cold to hot, is the cold getting colder because of the heat that it lost?
Yes, if heat comes out of this cools. And that's getting warmer. Point, think of your water. I want to make tea. So I got an oven that does work, or your microwave that does work. Heat goes in, and we heat it up. Yeah, this looks like two different things, but your refrigerator makes more sense. You're moving heat around. Yes? Oh. Heat cannot flow from a cold object to a hot object by itself. Naturally, spontaneously, take your pick. Only if you put work in. The second law has more ways to state the fact. This gets us right to a heat engine. It's any device that uses heat as input and supplies mechanical work. So you put heat in and you get work out. That's a heat engine. Like a refrigerator, an air conditioner. It's trying to cool the hot food, right? Yeah, you can let your food just sit there naturally and cool off because it goes from hotter to colder, but you don't want that. You want to speed things up. And so you have to do work to either speed it up or get it to go the way you want it to. Air conditioner, you want to make it colder? Well, you got to do work. That's the point. A heat engine does that. It's just refrigerator and air conditioner and examples. A heat engine can be one that uses work as input and moves heat uphill. That's what we just talked about. It's the same concept. Doesn't mean to be two different things. So let's draw it a different way to help clarify. Got our hot and cold reservoir. If we take heat out of the hot one, don't draw this. Or you can, but you'll have to redraw. That is allowed by the first law of thermodynamics. Heat comes out of the system and does work. And the same amount of heat that came out does work. Do you see how energy is conserved here? That does not violate the first law of thermodynamics. What it does violate is the second law. The second law, and another way to think of it, is that you cannot convert all heat to useful work. Some of it is always going to be wasted. Now you can write. Whoop. That'll be skinnier. So heat can never be 100% converted to work, is another way to think of the second law of thermodynamics. Heat can never be 100% converted to work. You'll always have some exhaust gases, some heat escape. And a lot of perpetual motion machines, this is where they falter. They forget about that. And if some of this is always leaving, then you seem to be having to put in more than you're getting out. And they're forgetting about this guy and conserving energy. Or they forget that, oh, somebody just shared an example, but he was on top of this. We're trying to make something do it and get work out, but that can't just do it all on its own. If you're constantly getting work out, there must be work in. If you're making this go uphill unnaturally, not the way it wants to go, you've got to be putting energy in. And so you can debunk about any perpetual motion machine that way. How efficient can they? Oh, yeah, how efficient can they be? Your book gives you a good way to do it. Ideal efficiency. So this, I just said, no heat engine can be 100% efficient. Do you see that? Well, how efficient can they be? This guy named Carnot, his last name, figured it out, a Carnot engine cycle. And we're summing it up in this chapter like this. Efficiency, in general, is energy in versus energy out. It's a percentage. That's what I get for not. That would make more sense. Energy out over energy in. If you put 10 units in and you get 10 out, it's 100%. You put 10 in and you only get 5 out, it's 50%. So that works for efficiency in general. The ideal efficiency for a heat engine can then be, look at it this way, want it to make sense. Usually we want a heat engine to do work. So what do? We add heat, some fuel or something. By conservation of energy, the work out has to be the difference. You're going to move heat in and out. This work is a form of energy transfer. Where is it getting transferred? Between the in and the outs, these reservoirs. It's going to be hot somewhere and make something else cold. They're going to change. I don't expect you to have to repeat this or memorize it. I just want you to see that energy out over energy in is efficiency. This is what we're looking at when we're looking at a heat engine. You want it to do work, you put heat in. How do you figure out that work? Well, it's the difference of the heat and where it moves. Bottom line is what the equation is in your book. This. I wrote it. There it is. Ideally, you can go further and relate these heats transferred to a temperature. And that's why it only works ideally. The difference between the hot and the cold side plays a big factor in how efficient your heat engine is going to be. The bigger the difference, the more efficient it will be. Jet engines use this. If you can make a jet engine burn hotter and hotter and hotter and hotter, then this side gets bigger and bigger and bigger. You get a bigger difference here. And so the same game plays, but just by this number, this ratio, your efficiency can increase. Does that make sense? Efficiency is energy out over energy in. And the way for us to look at that is these temperature changes. And the bigger that temperature difference, the more able it is to be efficient. There could be other problems with your system, your engine, but that's an important factor. So if it's 110 degrees Fahrenheit outside and you turn on your air conditioner, maybe it's going to be more efficient. It has to work harder too. The smaller the difference between the outside and the inside, it doesn't have to work as hard, but it's probably less efficient. All else being the same. Yeah?
Just trying to keep it as simple as possible. Just an electric fan, turning the fan on in a warm room. If there's moisture, some humidity, I assume it would help cool through evaporation. But you'd also have heat from the motor, which I guess would be a waste.
Now you're conserving energy. Yes. So a fan in a room, maybe there's moisture. It gets the air moving, and so you get evaporation, and that helps cool the room. But the motor's doing work. And so work comes out on the air, it's doing the system. Yeah, you're going to get exhaust heat, and the motor helps to warm up the room. And so, yeah, they're competing. There's a great question about your refrigerator. Can you cool your room by opening your refrigerator door? What, it's cold inside. If there's no airflow, it just warms up. Well, I know, though, if I stand right in front of my refrigerator with the door open, I get cool. Yeah. Where's it taking the heat from these your food inside? It has to put it somewhere. Does it put it back into the food? No, because the food gets cold. Doesn't do it inside the refrigerator. It pumps it out in the back of the fridge. I think we mentioned that earlier before. And that's in the room. So, okay, but now the refrigerator's open to everything in your room. So it's going to pull heat out of me, right? I'm hot and it's taking my heat, but then it just pumps it right back in the room, right? So now maybe we think the room doesn't change its temperature at all. But in reality, the room would actually get warmer. Because in order for that heat engine, or your refrigerator, to do that, there's going to be exhaust, because no heat engine is 100% efficient. And so as it tries to cool the whole room, which has an effect of cooling, it dumps heat back into the room. But it exhausts some of its own heat because it's working to do that in the first place. So the room will actually eventually get warmer. I know well, you might all know some people that have tried it. You back your coils of your refrigerator back to a window or an open door so it's out of the room. Then maybe you could cool the room eventually, but not much. Because now the heat, it's still the same game's happening, but the heat's escaping your room, your system. I don't suggest it because you'll burn out your coil and have to replace it in your refrigerator. That's what happened to my friends. Repeatedly. So, go ahead, Kate.
To stay on this,
A water heater, is that what you said? A water cooler.
So you've got water being forced into the fan.
Yeah, that's right. If you're
Air being forced over the water by a fan. That's work.
like a swamp cooler, yeah. Air over water.
And if you're in a dry climate,
It's less effective if it's dry.
cool.
Oh, yes. If it's dry. Yeah, we have swamp coolers a lot in Utah. It's a perfect example. That's what's on my house. That's a fan blowing air across something wet. It evaporates, helps cool. But if the relative humidity is high, like in Oklahoma or Kansas where I grew up, it's already full. So it's trying to evaporate, but it can't evaporate because the air can't hold anymore. It's saturated. Yeah, and around your house, or at least the swamp cooler, it might have reached the dew point, Yeah, no more can happen, and so there will be less evaporation and less cooling. Yeah, good example. Let me give you an example of this. Let's say it takes a heat engine, takes in 1,200 joules, and it does 400 joules of work. What's the efficiency of this engine? 33%, very good. Because efficiency is the, in this case, work out, Q in, write it out, 400, 1,200, get it right. Get out of the way. So it's energy out, energy in. We got this much out, we had to put that much in, so it's only a third efficient. Another example. Let's just do it here. Let's take in steam at, what did I say? 400 degrees Celsius. And it's going to release steam, there's exhaust, at 120 degrees Celsius. This one's a little trickier. Efficiencies H minus C. We can plug in those numbers, but I do this example to teach you that, as the book says, when you're dealing with heat engines and these temperatures need to be the absolute values. Which scale is that? Fahrenheit, Celsius, or Kelvin? Kelvin is the absolute scale because you have absolute zero. So in this, I would need to convert these to Kelvin. Do you remember how to do that? 400 plus 273. Remember, 0 degrees Celsius is 273 Kelvin. Or absolute zero is negative 273 degrees Celsius. They differ by 273 degrees. So if you do that, and then you got minus the other one, 120 plus 273. And divide all that by the other one. I'll write it out so you can see. That works out to be anyway, my point is this is the efficiency equation. We have a temperature difference between the two. Certain temperature steam comes in, other comes out. We can use that to figure out the ideal efficiency of this engine. We just have to make sure we're using absolute temperature values is all I wanted to really emphasize with this and show you how this works. So you can plug all that in, and this comes out to be about 42% efficient. Ideally, at best. That's the second law. Yeah?
I get that you have to use the absolute temperature scale, especially on the bottom, but on the top doesn't just cancel out. Because you have to add 273 to both of them, and then you just minus it anyways.
Good observation. You are right. It confuses more people, though. You don't want to say, oh, you can use Kelvin or Celsius on the top, but you have to use Kelvin at the bottom.
No, you have to use Kelvin on both. I just said that it's going to be the difference.
Well,
By how much Kelvin you have on top.
yeah, on the top, it's the difference, right? And you've noticed that the increments of degrees in Celsius and Kelvin are the same. So if you put that difference in, you get the same change. And so you can, mathematically get it to work that way. I just don't want to confuse folks. Just keep it all in Kelvin and then you never go wrong for efficiency. Let's go back to this. This, the first law, speaks of quantity of energy. We got to keep it conserved. We pay attention to where it goes. This one speaks of quality of energy. This leads us to entropy. If a heat engine can never be 100% efficient, because you're always going to get some heat escaping or lost, then we can never convert heat 100% into work. It's always becomes less useful. So quantity is always conserved, but some of that energy becomes less useful. The quality goes down. And entropy, write that word, is a measure of disorder. It's defined in your book, but that's how I like to think of it. It's a measure of disorder. It's an indicator of how much energy is not available to do work. Because some of it is just not that useful. It's degraded so much in quality that you can't use it. Entropy is on average increasing in the universe. Everything's becoming slowly and slowly more disordered, less and less useful to do work. That's what entropy is. So that's another way you can think of the second law. It speaks of the quality. As energy transforms, it becomes less useful. Make sure I get this all to you. Organized energy degrades into disorganized energy. You could redraw this picture. Oh, it's over here. You can think of this as disorder to order. In order to get more order, out of something, you got to do work on it. Things naturally want to just go to disorder. If you want to organize it back in, you're going to have to do a bit of work. I got an example of that. Couple. Marbles and beads. Right now, I'd say they're pretty organized. The entropy is low. I'm going to mix them. Did the entropy increase or decrease? Yeah, it increased. They're now mixed up. They're more disordered. And we've just contributed to the less useful energy in the universe. So how do you get them back separate? Filter. And I'm going to do it because somebody asked for this once. That's all they thought about. And then in the back room I'm like, oh man. Well, I at least made a little filter and tried to make my job a little easier. But, so you pour them in here. I can try to separate. I learned to pour them in here first because that's glass and these are glass and they break. Static electricity. That's the next unit. Good enough for our purposes. It's proving a point. Ta-da! Do you see how much work I had to do to cause more order? That's the second law. That's entropy. It naturally wants to go to disorder. If you're going the other way, it's harder. It takes more work. And did I do it great? in the process of doing it, I did work. I'm like a heat engine, biologically, chemically. So what came off of me while I was working? Heat. I just exhausted heat. So in me trying to make more order, I actually caused some disorder myself. Dang it. So another way to think of the first law is you can't win. You're never going to get more energy out than you put in. It's impossible. The second law, you can't even break even. Because nothing's 100% efficient. And as hard as you try, you're always causing disorder. You can't make a 100% efficient engine. You're always going to have something escape. Something's going to become more disorganized and less useful to do work. All right. This one. Pretty much got through the topics. I was going to relate them to a few demos. We can do that Monday in the review. So I'm going to pound this lid on. There's a hole in the bottom and a hole in the top. I'm going to attach it to the natural gas down here. Put some inside. I'm listening for it. There it is. That should be enough. Light it. Turn off, dim the lights a little here. Do you see that flame? Nobody? I can see it. Can you see it? Okay, good. This is a convection. It's heating up, the gases come out. Well, the cold fresh air comes in. The oxygen mixes with the methane, natural gas. And it burns. Anybody's birthday today? We can sing to you. So we have a constant thing happening here. Heat's escaping. It's heating up the gas inside. It's doing work on the system. We have convection going on. It's a good review. But I'm using this for entropy. I'm constantly letting heat escape. These two gases come together and mix, and then I'm burning them. So it's like this on steroids. When that gas, as it uses up the methane, the flame gets smaller. And if that flame goes inside the can, what do you think happens? Camera, you can stay on the can. I'm not exciting. Yeah, it explodes. Because it heats up the gas inside. Hey, energy in. Energy got to come out, work on the system, it expands, and boom. We just caused a lot of disorder. Explosions are disorder. Increase the entropy. There is nothing I can do to gather that methane and oxygen back together and separate them back out, stick it back in the line. This is an irreversible process, and I've just contributed to the heat death of the universe. That's entropy. Have a great weekend.